You might ask, can we use the fundamental theorem of calculus to write the equation for the position function at time t in terms of the velocity function? And the answer is yes. We already know that the velocity function is the derivative of the position function. So we know that the antiderivative of the velocity function is the position function, or at least an antiderivative of the velocity function is the position function. The question is, which one? Well, we can actually figure this out using the fundamental theorem of calculus. So we know that if we were to integrate from a to b of the velocity function, we would get the displacement between a and b, s of b minus s of a. In particular, that tells us that the integral from 0 to t of the velocity function, in terms of some other variable, why don't we call it x, is going to be the position at t minus the position at 0. Since the position at t is actually what we're interested in, we can actually solve for this and get that the position of t is equal to the initial position plus the integral from 0 to t of the velocity function. You can think of this another way too. You can think of the position at any time t is equal to the initial position plus the displacement. So wherever you started from plus however far you are currently from where you started, which should make good sense. So we can actually use this to quickly and easily calculate position functions if we're given the velocity. For example, if we have a nice simple velocity function like v of t equals 5t, then the position function is going to be whatever the original position was plus the integral from 0 to t of 5x dx. Now note that we can't actually find this position function unless they give us an initial condition. So let's say they tell us that the velocity is 5t and we're going to start at 12. Now we know that s of t should be 12 plus the integral from 0 to t of 5x dx. So that means s of t is 12 plus 5x squared over 2 from 0 to t, which means s of t is equal to 12 plus 5t squared over 2 minus 0. So we don't even need to put that part. So now we found our position function. And notice that we didn't have to solve for a plus c. So it's a little bit quicker than just solving an initial value problem with an antiderivative. Also, if they were given a different point instead of s of 0, you could actually make this whole equation work for another point. So you could say, if they gave you, say, s of 3, say s of 3 was 5, then you could say that the integral from 3 to t is s of t minus s of 3, and so s of t would be s of 3 plus the integral from 3 to t. So you can actually do this for any point you want, although we almost always do it for 0. Similarly, you can do the exact same thing to get velocity from acceleration. The integral from 0 to t of the acceleration function, in terms of some other variable, let's say x, is the velocity function at t minus the velocity function at 0. So solving for v of t, we get that v of t is the initial velocity plus the integral from 0 to t of the acceleration function. This works exactly the same way as before. And finally, we can say the same thing for any equation. Say we want to know some quantity q, and we want to know how it changes with time t. Well, if we know the rate of change of q, then we can say that the integral from 0 to t of the rate of change of q is equal to q at time t minus the initial value of q. So the quantity at some future time t is equal to the initial quantity plus the integral from 0 to t of q prime of some dummy variable like x dx. So to summarize, the future value of some quantity is just the initial value plus the integral from 0 to t of q prime of x. And the net change of that same quantity is the definite integral from a to b of the rate of change of that quantity. So that's kind of like net area or displacement. It tells you how far has the quantity changed from one time to another without paying attention to what it's doing in between. So, for example, if somebody told you that the number of Starbucks in a certain region was growing exponentially, and they were telling you then that the quantity of Starbucks is changing at a rate of, say, e to the 5t. And if there are currently, we'll call this time 0, 12 Starbucks in your town, let's say t is in years, how many Starbucks will there be in 3 years? Assuming that, Starbucks continues to grow at a rate of change of e to the 5t. Well, the quantity of Starbucks at any time t is equal to the original quantity plus the integral from 0 to t of the rate of change of the quantity. So the quantity of Starbucks at any time t is equal to 12 plus the integral from 0 to t of e to the 5x dx, which is that the quantity at any time t is 12 plus e to the 5t divided by 5 from 0 to t, which means that the quantity at any time t is 12 plus e to the 5t over 5. Now be careful here because e to the 0 is 1, not 0. So it's e to the 5t over 5 minus 1/5. This means that the quantity of Starbucks 3 years from now would be 12 plus 1/5 e to the 15th minus 1, which is approximately 613,815. That's a lot of Starbucks. So let's hope that the rate of growth of Starbucks is not really e to the 5t. Or maybe if we know that this is the current rate of growth of Starbucks, or maybe some kind of bacteria or something that we don't want, and we can see that 3 years from now we would have this many of them, maybe we want to take action now to decrease the rate of growth so that this doesn't happen.